We know that the periodic table is one of the most predictive tools in science. We're going to be looking at the periodic trends based on the periodic table so that we can have a better understanding of how all the elements react together. We're going to look at atomic radii, ionization energy, and electron affinity. If we think about the atomic radii, we're going to look at the periodic table in two directions. The group going down, as we talk about families and groups, such as the main group element 1A, and then period. A period will be using the same energy level and going from left to right on the periodic table. If we look at going down a group, the atomic radii is going to increase. This makes obvious sense. We're adding more and more electrons, and as we add electrons, we add more and more shells, and these shells are going to increase the size. If we look across the period from left to right, we see a decrease in atomic radii. This doesn't make sense. We have increased the number of electrons, but the size is getting smaller. To understand this, we need to look at a phenomenon. Our Z effective, our effective nuclear charge. It turns out as our nucleus is increasing in the number of protons, so as we go from left to right in the periodic table, we are adding the number of protons in the nucleus. As this occurs, we're having a higher effective attractive force on the outer electrons. This is the Z effective. So as we go from lithium to fluorine, our Z effective is increasing. Therefore, the attractive force pulling in those electrons has increased. That explains why when we go across the period from lithium to fluorine, we go from a larger atomic radius to a smaller atomic radius. It's important to understand when we learn our periodic trends, the basis. The basis going down a group for atomic radii is the fact that we're adding more electrons and getting more shells. The basis for why we decrease atomic radius as we go across the periodic table is the fact that we're actually increasing the Z effective, the attractive force that pulls in those electrons. When we look at ionization energy is defined as the energy required to remove an electron from an atom to make an ion, a cation. When we look at ionization energy, the general trend is that it's going to be increasing across the period, going from left to right. It's going to be decreasing in energy as we go down the group. That makes perfect sense. As there's more and more electrons, it should be easier to take an electron out of the system. Going across the period, that also makes sense, because as we go from one electron to two in those outer shells, it should be harder to remove the next electron. There are a couple of hiccups in this ionization periodic trends. And that is when we get to fully filled orbitals, so as the S2, and the Hef-filled, such as the P3. At these points, we see a small deviation in our energies. We see the same type of trends when we get to electron affinity. Electron affinity is the amount of energy released when an electron is given to an atom. So if we look at chlorine, if I give an electron to chlorine, how much energy will be released? If we think about this one, we should see a greater electron affinity for halogens because they're only one electron away from our noble gases. This is the trend we see. But like the ionization energies, we see small variations when we get to fully filled S, and half-filled Ps, and half-filled Ds. Using the periodic trends can help you understand the reactivity of the elements, understand their physical property, size of the ions, the amount of energy required to either add or remove an electron. It's important for you to understand the periodic trends because using the periodic table to its fullest amount will make your journey through chemistry much simpler.